Today we are going to talk about IPv6. With the development of 5G, cloud services and IoT, a series of new technologies such as SRv6, network slicing, new mount cards, and in-band fault measurement have emerged. These technologies can meet the requirements for connectivity of everything. One network to multiple clouds, intelligent connection, and intelligent ORM, implementing agile network adjustment upon cloud changes and intelligent connection of everything. These technologies are collectively referred to as IPv6+ in the industry. But how does IPv6 support IPv6+? Today we will explore IPv6's potential for innovation to uncover why IPv6 is an inevitable choice for next-generation networks. Today's introduction to IPv6 basics focuses on the huge innovation space of IPv6, covering the definition, advantages, and design ideas of IPv6, as well as types, functions, and applications of IPv6 extension headers. First, IPv6 is a second-generation network layer protocol and an upgraded version of IPv4. It is well known that the biggest problem of IPv4 is its insufficient address space. All IPv4 addresses were exhausted in 2019. Some people may wonder why IPv4 is not followed by IPv5. IPv5 is an experimental resource reservation protocol that aims to provide service quality. IPv5 inherits the 32-bit addressing of IPv4, so insufficient address space is also its fatal problem and is abandoned before it becomes a standard. When it comes to IPv6, the inherent impression is that it has a large address space. Does IPv6 early solve the problem of insufficient IPv4 address space? Obviously not. What advantages does IPv6 have in addition to expanding the address space? In terms of packet processing, the IPv6 packet format is designed to simplify the basic header. In most cases, a device only needs to process the basic header to forward IP traffic. Unlike the IPv4 header, the IPv6 header does not carry the fields related to fragmentation, checksum, and options, but it carries the floor label field. This simplifies IPv6 packet processing and improves processing efficiency. In addition, IPv6 utilizes extension headers to support various options without requiring modification of the existing packet format, offering exceptional flexibility while keeping packet headers simple. In terms of address maintenance, IPv4 mainly depends on DHCP to provide address auto-configuration and readdressing. IPv6 provides its own address auto-configuration to allow hosts to automatically discover networks and obtain IPv6 addresses, improving network manageability. In terms of end-to-end security, the original IPv4 framework does not include it, whereas IPv6 supports IPsec authentication and encryption at the network layer. In terms of queues guaranteeing, with the popularization and application of network audio and video, flow labels are added to IPv6 to provide better queues guarantee. In terms of mobility support, IPv6 can use the neighbor discovery function to directly discover a foreigner network and obtain a key-of address. In addition, the mobile and peer nodes can directly communicate using the routing and destination options headers. Triangular routing and source address filtering in mobile IPv4 are no longer issues. In terms of route summarization, the enormous number of addresses provided by IPv6 allows us to design networks hierarchically, facilitating route summarization and improving forwarding efficiency. Next, let's start with the IPv6 packet structure to understand the design ideas of IPv6. An IPv6 packet consists of three parts: an IPv6 basic header, one or more IPv6 extension headers, and an upper layer PDU. An IPv6 packet uses the next header field to identify the next extension header or the type of upper layer protocol. If multiple extension headers are used, the next header field is used to indicate the type of the next header that follows. An upper layer PDU is usually composed of an upper layer protocol header and its payload. The PDU can be an IPv6, TCP, or UDP packet. Currently, many IPv6-based innovations are implemented by modifying extension headers. What are the advantages of doing so? The structure of the IPv6 basic header is not changed. In most cases, a device only needs to process the basic header to forward traffic, ensuring IPv6 reachability. Moreover, an IPv6 extension header can be of any length and can theoretically be extended indefinitely, offering excellent flexibility and huge space for innovation. Now, let's learn about the types and functions of IPv6 extension headers. As defined in RFC 8200, IPv6 has the following extension headers: hop-by-hop options, destination options, routing, fragment, authentication, encapsulating security payload, and upper layer headers. The hop-by-hop options header is used to carry information that needs to be processed by each router on a forwarding path. The next header value is 0. The destination options header is used to carry information that needs to be processed by the destination node and the node specified in the routing header if it appears before the routing header, or is used to carry information that needs to be processed by the destination node if it appears before the upper layer header. The next header value is 60. The routing header is used in a resource routing scheme to specify the sequence of nodes that a packet passes through on a network. The next header value is 43. The fragment header is used when the length of a packet sent by the source node exceeds the path MTU and the packet is fragmented. The fragment header carries the identification information of each fragment. During reassembly, the identification information is used to select all fragments of the same original packet and their sequence. The next header value is 44. AH and ESP are used for IP authentication and encryption, but AH supports early authentication. The next header values of AH and ESP are 51 and 50, respectively. The next header values of upper layer protocol packets, such as IPv6 and UDP, are 58 and 17, respectively. Next, let's look at the applications of several IPv6 extension headers. First, SRH is used for SRv6 to implement SRv6, a new type of extension header. SRH is defined based on the original IPv6 extension headers. If the value of the next header field in the IPv6 basic header is 43, the next extension header is the RH. If the value of the routing type field is 4, the type of the RH is SRH. The SRH carries segment lists and other related information to explicitly specify an SRv6 path. the destination address is updated according to the SL pointer offset, and the forwarding is completely segment by segment. Next, the HBH options header is used for network slicing. In network slicing scenarios, the HBH options header of an IPv6 packet carries slice ID information to specify the slice over which the packet is carried. As we can see, the value of the next header field in the IPv6 basic header is 0, indicating that the next extension header is an HBH options header. The value of next header field in the HBH options header is 43, indicating that the next extension header is an RH. The slice in this scenario is an SRH-based network slice. The HBH options header is used to carry information that needs to be processed by each device on a forwarding path, and the slice ID is encapsulated into HBH options header. Network devices along the packet forwarding path use the slice ID to identify the target network slice, and then forward the packet according to the rules specific to the network slice. In another application, the IPv6 DOH is applied to BRv6. During forwarding, a device reads the bit string in a BRv6 packet to determine the next replication node, and updates the destination address of the IPv6 packet based on the bit string. In this way, the entire forwarding process is presented as native IPv6-based source routing multicast. The IPv6 DOH is used to carry information that needs to be processed by the node of the destination address. In the BRv6 solution, the bit string is encapsulated into DOH to identify a set of destination nodes of a multicast packet. In addition, the IPv6 source address is used to identify the source of multicast packet. In this manner, BRv6 multicast packets can be replicated and forwarded based on the IPv6 header. Finally, the HBH options header, or SRH, is used for IFIT. The IFIT instruction header can be encapsulated in the IPv6 HBH options header or the SRHC's optional TLV. In the packet forwarding process, IOM information is forwarded together with packets to complete measurement. All IPv6 forwarding nodes can process the IFIT instruction if it is encapsulated into HBH options header. In SRv6BE or SRv6TE policy loose path scenarios, where the packet forwarding path is not fixed, encapsulating the IFIT instruction into the HBH options header helps O&M personnel to know how packets are forwarded hop by hop and facilitates fault locating when a fault occurs on the network. If the IFIT instruction is encapsulated in the SRH, only the specified endpoint can process it. This approach is suitable on legacy networks, as it allows O&M personnel to perform on-path network telemetry on the specified feed-capable nodes. In SRv6TE strict path scenarios, the encapsulation effect is the same as that of IFIT instruction in the HBH options header. Even after over 20 years of development, IPv6 has not yet been widely deployed. Address insufficiency is not enough to drive the deployment of IPv6. The story may change after the advent of SRv6 as new services continue to develop. SRv6 is no longer the early technology affecting IPv6's future. Specifically, the data plan supports extensions of other types of IPv6 extension headers in addition to SRv6 SRHs. As we've just talked about a few applications, network slicing implemented based on the HBH options header, BRv6 implemented based on the DOH, and IFIT implemented based on the HBH options header, or SRH. The industry defined these as IPv6+ and its 3 development phases, which were expected to support new services through network programming, revealing the characteristics of the new era of IP networks better. With the development of 5G and cloud, SRv6 is ushering a new era of IPv6 applications. As the cloud and network become more converged, more information needs to be exchanged between them. With IPv6 being the most advantageous choice to achieve this, new research topics and solutions may emerge during IPv6+ development. Without question, the IPv6+ era has just begun. We look forward to your exploration and innovation. That's all for today. I hope we've piqued your interest enough for you to get involved in IPv6 and its huge space for innovation. And we look forward to more exploration and innovation that will promote the deployment and application of IPv6. Thank you for watching.